Hello everybody. In this video we're going to learn about significant figures. Sometimes we shorten that to be called sig figs because we don't want to have to say the whole phrase. Significant figures are what we're going to use to try to account for any level of uncertainty in our measurements due to the equipment that we use in labs. So anytime we have to estimate a number, that means that that number is a little bit uncertain. Every measurement is going to be a little bit uncertain because our equipment is not perfect. Our instruments that we use in the lab are not going to have an infinite number of decimal places. At some point, our last digit is estimated a little bit. And we need to keep track of that because those levels of uncertainty can kind of build upon each other and can really change how accurate your number is. First, we're going to look a little bit at the difference between precision and accuracy. People often use these interchangeably, even though they are technically different. So accuracy refers to how close the number is to the actual true value, okay? How close is it to the correct number? Precision refers to how often are your measurements going to be close to each other, okay? So if you look at these little targets up here, I think this is one of the best ways to understand the difference between these two terms. This target here is precise because these arrows are close to each other, but it is not accurate because it did not hit this bullseye. In this one, it is precise and accurate. So the arrows are close to each other. We're getting the same thing over and over, and it's the correct value. It's hitting that bullseye. This last one is not accurate and it's not precise. The arrows are not next to each other. We're not hitting the same place every time, and we're not getting them where we should either. So accuracy is how correct is your answer. Precision is kind of how much can you repeat it and get the same number every time. You want your values to be accurate and precise. We want the correct answer, and we want to get the correct answer every single time. So hopefully, if you have good equipment, you will have a fairly accurate measurement, and you should get the same number repeatedly, no matter how many times you measure it. So the sig figs are what kind of counts the level of uncertainty in our measurements. So we're going to kind of go through some rules for how we count significant figures. We're going to go through some rules for how you use significant figures in mathematical operations. It does take a lot of practice to get comfortable with significant figures. If an answer ever needs significant figures, I will make sure to tell you that on a quiz or a test. It is important that we know how to use these, but not every question will require it. So any number that is not a zero is always going to be considered significant. So, excuse me, so if this is our number, 3, 4, 5, 6, this has 4 significant figures. All of these digits are non-zero integers, so they all count, they all matter. Leading zeros never ever count. These are zeros that come in the beginning and are basically just placeholders. So if this is our number, you can see here that these zeros in the front do not actually count as significant. They are simply there as placeholders. So this number only has 3 significant figures here. Captive zeros are zeros that are stuck in between the actual real integer numbers. So they always count as significant. So if you look here, we have a 0 that is held captive. It is trapped between the 6 and the 7. So because of it being trapped between two numbers, it will count as significant. So this 0 we know is accurate, so we make sure that it counts as significant. Trailing zeros are zeros that come at the end of a number, and these are a little trickier because there's going to be some different types of trailing zeros. They sometimes count as significant. If they are after a decimal, they always count. If there's no decimal, they do not count as significant. So here you can see 9.300. Because there's a decimal here, we are going to count all of these as significant. Compare that to 9300 with no decimal anywhere. That means these trailing zeros at the end don't count. We don't care about them in terms of significance. We don't really know, is this 9,301? Is this 9,340? We don't really know what these digits at the end are. They were estimated. So the 3 is the last digit that we really know with some level of certainty. So this only has two significant figures. Another type of number that oftentimes people don't really think about is something called an exact number. So an exact number has an infinite number of sig figs because it is not estimated at all. It is an exact known quantity. So for example, if I tell you that there are 12 inches in 1 foot, you're going to know that it is exactly 12 inches in 1 foot. If I tell you that there are 12 eggs in a dozen, it's not 12.01, it's not maybe, 12.2. You know for sure it's exactly 12 eggs. And so it is an exact number. If I ever give you an equality statement to use as a conversion factor, you can assume that it has exact numbers. We will not use our conversion factors in terms of our significant figures because, sometimes conversion factors are rounded, sometimes they're not, they're exact. It gets a little bit tricky. So if I give you an equality statement like this, you can just assume that it is an exact number. So let's do a little practice. In this number, how many significant figures do you think there are? Write the number down in your notes and then write your best guess. All right, the answer is 5. There are 5 significant figures here. These are captive zeros, so they count. The 0 at the end came after a decimal, so even though it's trailing, it does count. And the 1 and the 7 are actual numbers, right? They're not zeros, so they always count. So these are all significant figures. Let's try another one. Write it down in your notes. Write down how many significant figures you think it has. All right, the answer is 4. We have a 1, a 7, and a 1. Those real numbers all count, right? This is a trailing 0. It comes after a decimal, so it also counts. All of these are significant. Let's try this one next. All right, this one's a little bit trickier. This number has 5 significant figures. The 1 counts. These are captive, so they count. The 8 and the 9 count because they're regular old numbers. Now this trailing 0 does not count because there is no decimal. So because there's no decimal, this does not count. We don't really know if this was, 100,891 or was it 100,897? We don't really know what this last digit was. So it means it's not significant in terms of our level of uncertainty. We can't know how certain that number was. All right, let's try this one. This one's a little bit tricky because it has scientific notation in it. This one has 3 significant figures. Our significant figures in a scientific notation are just these ones right here before your multiplication. If I were to expand this number and move my decimal 3 times, any zeros at the end up being not significant because they're trailing zeros. So we can use significant figures and scientific notation all in one problem because we understand that the numbers in front are the ones that are significant. The times 10 to the exponent we don't care about when we're trying to count our significant figures. Okay, try this one, a number that's less than 1. So this only has 2 significant figures. All these zeros in the front are leading zeros. Remember, leading zeros do not count as significant. They are only there as placeholders. So we have the 5 and the 4 that count. All right, try this one, a really big number. 3,200,000. Huge number. But does it have a lot of significant figures or not? These are all trailing zeros. And I don't see a decimal anywhere here. So these trailing zeros do not count. So we only have 2 significant figures. Let's try one more. I know it's a lot of practice problems for the notes, but there's just so many varieties of numbers you might see that it does take a lot of practice problems to kind of be exposed to the variety of things you might come across. So here's another one. All right, these are leading zeros, so they don't count. The 5 and the 6 count. The captive 0 that's trapped here counts. The 3 counts. And this trailing 0, because it came after this decimal, it does count. So this number has 5 significant figures. Counting significant figures is not too tough because you do end up using them often enough that you get really used to counting them. But doing mathematical operations with significant figures is a little bit trickier and it does take some practice. Multiplying and dividing, what we're going to do is our answer is going to be limited by the least number of sig figs that you see in the problem. So you're basically going to be limited by your worst number. So when I do this number in my calculator, I do 6.38 times 2.0, out pops this answer. However, this is not my final answer. because this does not take into account the level of uncertainty, the rounding that I used in my equipment. When I look here, this has 3 sig figs. That's a pretty good number. This one only has 2 sig figs. So whatever my answer is going to be limited by the smallest sig figs that I see. So that means I have to round my final answer to match the number of sig figs from my worst number here. So I'm not going to say 12, right? Because this doesn't round to 12. This would round to 13, and that would be 2 significant figures. Sometimes your answer will end up smaller. Sometimes it will end up bigger. It just depends on the rounding and the number of sig figs that you can use. So give this one a try. Punch that in your calculator. Or, if you notice, these are all basically the same answer with different number of sig figs, right? And if I look up here, I can see instantly that I'm limited by 2 sig figs because of this 7.0. So I know instantly that my answer has to be B because it's the only one there that has 2 sig figs. I don't know my number well enough to know if it's 22.7 or 22.6. I have too much uncertainty for that. I have to guess that my number is about 23. So I'm basically having to account for any unknown in my answer. So try this one. You don't need to do it in your calculator. Just base your answer off of the number of sig figs you should have. We're multiplying and dividing, so we should have the least number. This has 4. This has 3. So my final answer needs to have 3 sig figs. So A must be my answer. Okay. Same thing, you do not have to punch it in your calculator. You can base your choice off the sig fig number. This one has 1 sig fig. This has 4 sig figs. These are leading zeros and they do not count. So my answer is limited by this one. My answer can only have 1 significant figure. I don't know it this precisely. I don't know, right? It's going to have to be rounded. People really don't like that your final answer may not match your calculator answer. But it is what it is, right? Our calculators don't understand significant figures. Our calculators are not that smart. This is a point where math and science really are a little bit separate from each other. In math, you may give that calculator answer with 18, decimal places listed. You're not going to do that here. Because these are measurements, we got to take into account the concept of this rounding. This one has kind of a tie, doesn't it? They both have 2 sig figs. Well, if it's a tie, it's not tricky. Your least number of sig figs is 2. So you would make sure that your answer gets rounded to 240. Sometimes people will ask, well, why didn't you just take off the ending and make it 236? Well, because that has 3 sig figs, you got to round it. So when you round to 236, it's going to round up to 240. Adding and subtracting is a little bit different. Adding and subtracting, we're going to base things off of the least number of decimal places. So a little bit different. So in this example, this has 1 decimal place. This has 3 decimal places. My calculator spits out this answer. but I need to adjust it to be based on the least number of decimal places. So instead of 18.734, I'm only going to write down 18.7. So looking at this problem, how many decimal places should my answer have? Well, we have 2 here, and we only have 1 here. So I need to make my number have 1 decimal place, which would be choice B. Here's another one. Now sometimes people start to mix and match. Wait a second, am I counting sig figs or am I counting decimal places? And I will literally write off to the side like, okay, it's addition. I'm doing decimal places, right? So this has 2 decimal places. This has 1 sig fig, but it has 2 decimal places. So I pick that one. For this problem, I have 3 decimal places and 3 decimal places. It's a tie, so my answer must be B. Now, things get a little bit tricky when you start doing more complex problems where you have multiplication and an addition, or maybe you're dividing and subtracting. So when you start layering these together, you have to do each piece of the problem separately. You remember, I don't know what the phrase is these days in math class, but we used to say, please excuse my dear Aunt Sally, which would tell us the order of operations. And so you kind of want to think of it like that, where you're going to clump your things together based on the order of operations. And what we're going to do is we're going to do some practice on worksheets, and you're kind of going to learn it through the practice because there's so many strange combinations of mathematical operations, decimal places, sig figs, that it's a little bit easier to actually remember it by just giving it a try. It's the best way to remember how to do it, best way to learn how to do it. I highly suggest that you use pencil because the lesson we're going to do is basically try it. If it's not right, we'll erase it and do it again. Okay? So it is a little bit uncomfortable for some people when we learn sig figs because there is so much, you know, variation in the problems. Sometimes they're super easy and sometimes they're really weird. You know, I'm not going to try to find the hardest, craziest problem out there and give it to you, right? I'm trying to see if you can do the general concepts, right, and apply it to numbers maybe you haven't seen before. You know, so don't look online and try to find the craziest, hardest problems there are and get really freaked out, okay? Just go off of the worksheets I give you. Go off of the type of problems I give you, the level of difficulty that I give you. This gets very complicated very fast. And I don't want you going out there on the internet and overwhelming yourself. Okay, so please realize that I make the worksheets and I kind of decide the level of difficulty and I present it to you based on our homework, right? So please keep that in mind for this topic. All right? Okay, everybody, I hope that was helpful. Bye.